Hey guys, Aldo Speed here. Today we're going to be looking at this medium problem, 1302, deepest leaf sum. So here we're given the root of a binary tree and we want to return the sum of values of its deepest leaves. So I'm looking at this example they gave us, and here we have this root of 1. So we're going to be passed in this binary tree with this root node of 1. And we want to essentially go through this binary tree traverse in such a way that we only account for the 7 and we only account for this 8. So when we're looking for its deepest leaves, we're not looking for just all the leaves, like, right? We wouldn't account for the 5. We just want the 7 and the 8. So deepest in this sense means deepest in terms of the levels within the binary tree. So when I'm thinking about collecting nodes of the same depth, the direction my mind goes in is BFS, right? BFS really lends itself as the correct algorithm in this case because it does a level order traversal of this binary tree, which is essentially what we want, right? We want to go through this binary tree. When we get past this node of 1, we don't know what the depth is, right? This is not a variable. We're given the tree node definition, class definition right here, and we can see that we're not given a variable or an attribute for the depth of this binary tree, and there's no way to instantaneously access the depth of this binary tree. So when I'm looking for the deepest leaves, I'm going to go in and just perform a level order traversal, right? So I'll go in, I'll see this 1, then I'll see this 2 and 3, then I'll see this 4, 5, and 6, and then I'll see this 7 and 8. So what's the most efficient way to just get the 7 and 8 without having any assumption about the structure or making any assumptions about the structure of the binary tree? Why don't we just go through, perform each level, and at each step, just replace what we had for the previous sum. So we're going to keep a sum, cur sum, or a variable called res or answer or current sum. And we're just going to sum the nodes at the same level using a standard BFS algorithm with just this slight modification of keeping track of the sum at each level. And I'm just going to repeat it, or I guess I'm going to replace it at each level each time I move on to the next level. So finally, when I've traversed my final level, I won't have any more levels, or any more nodes left to traverse, so I won't replace the current sum variable, and then at the very end of the algorithm, I could just return this current sum variable. Okay, so let's jump right into the code. The very first thing I'm going to do is I want to import a deck. And why do I want to import a deck? This is because in Python, when we do a BFS traversal, we want a queue data structure, right? And in Python, the way we do that is by using a deck, a double-ended queue, because we need this pop left operation, an operation that allows us to access nodes from the very beginning of our queue. So let's do that with from collections import deck. And let's just jump right into the meat of the algorithm. So I'll have a variable that's going to be my queue data structure. So this is my deck. And since this is the very beginning of the algorithm, I'm going to populate it with the variable root. And root, by the structure of any binary tree, root is the only variable at its most shallow depth, right? So it's going to be the only thing at this deck. And as we talked about, I want to keep a custom variable. I'm going to initialize this to 0. So while I have elements at my current level, then this means I need to pop and then add more. I'm going to say, first, I'm going to reset my custom because this means that I have elements to pop off. This means that the previous custom did not contain the deepest nodes in my binary tree. So I'm going to say custom equals 0. Now in order to just collect all these nodes at the same level at the same time, I'm going to have a variable num nodes, and this is going to be the length of my current level, my deck at this current moment, which essentially tells us the number of nodes at the same level of this binary tree. So for I'm just going to do a quick for loop to iterate over all these nodes. And so now that I have my current node, I want to add to my curve sum the node val. And so now if you notice, the way I've structured this algorithm essentially resets curve sum each time, right? So now I don't want to add none nodes to my deck, right? I want to check if there is a left child and a right child to add. And if there is, then I'll add those children to the deck. Oops, I want to say cur node dot left. Okay, finally, now that I've done all that, I can return my cur sum. So this should work. Let's run it and see if it does. It gets accepted and gets accepted. So great. The runtime for this algorithm will be O of n because we're going to loop through and visit each node in our binary tree. So if n is the number of nodes, our runtime is going to be O of n. And the space complexity, we have this deck where we keep track of the num nodes. So this will also be O of n, even though it won't grow to the size of O of n. Even though it won't contain all the nodes at this very exact same time, we're going to say O of n because that's the tightest bound we can give it. Okay, I hope that helps. I will see you guys in the next video.